Okay, this next question is going to touch on both principles of conservation of energy. The first part of it is without losses, and the second part of it is with losses. So start off by reading it. You've got a 2 kilogram block sliding down a frictionless curved ramp. That's how we know that there aren't any losses, because it says frictionless curved ramp, and it starts from rest at a height of 3 meters. The block then slides 9 meters on a rough horizontal surface before coming to rest. So we know it's coming to rest, and the cause of it is this rough horizontal surface. And he's going to slide for 9 meters. Uh, First part, we want to know the kinetic energy and speed of the block at the bottom of the ramp, and then we'll figure out the work loss due to friction and the kinetic coefficient of friction. But first, you need to kind of understand visually what's going on here. So we have a picture drawn here of the curved frictionless ramp. So this part is frictionless. And then this part here is the rough part. Okay, so drawing it in as if it's the rough surface, so we can distinguish between the two. Okay, frictionless, rough surface. Okay, and we need to figure out what the speed is at the bottom of the ramp and the kinetic energy at the bottom of the ramp. So we've kind of have a situation here where we have position A, B, and C in this problem. So we're going to go ahead and label those position A, B, choose another color for B, and C. Okay, so we can probably figure out our potential energy at A. The reason we can figure that out is we know the height at A. And we're going to start from rest, so we'll know our kinetic energy at A. So potential energy at A, we'll use at A, we'll use mgh. We've got a 2 kilogram block, so we know the mass. We can figure out potential energy at A. 2 times 9.81 times 3, and that will give us our potential energy at A, which calculated would be 58.9 joules. And we know we're starting from rest, so we know the kinetic energy at A is equal to 0. Why? Because the velocity is 0. If there's no velocity, there is no kinetic energy, joules. Okay, so those are our two energies at A. Now we can figure out our energies at B. Well, we were calling this our 0 line. Probably should have specified that in the beginning, but we are calling this our 0 line. And we can call that our 0 line because we know this is 3 meters and there. So we have that drawn. And this is 3 meters. This is our 0 elevation line. So our potential energy at B here reaches our 0 elevation, so 0 elevation or 0 height means potential energy at B is equal to 0. And because this is a frictionless curved ramp, because this is frictionless curved ramp, then this equation applies. And we can put in our energy equation, and that looks like this. So here's our energy equation, or one of the variations of our energy equation, and we know there's no workout because there's no friction, okay, and the potential energy initial is the A, so our initial is A, potential energy initial is 58.9, and we're going from A to B, plus kinetic energy initial, that's 0, equals potential energy final, that's 0. That's the potential energy at B, plus kinetic energy final, which we are trying to find the kinetic energy at the bottom of the ramp. Kinetic energy final is what we're trying to find. And hey, look, kinetic energy final plus 0 is kinetic energy final. And this is a situation where kinetic energy final is equal to your initial potential energy, which is 58.9 joules. With this information, we can solve for the the velocity final, kinetic energy, the velocity at this part B. Use the kinetic energy formula. Kinetic energy at B we have is 58.9. Mass we have is 2. Solve for velocity at point B. Plugging numbers in, solving for velocity at B. Velocity of B is equal to 7.67 meters per second. The next part asks us, what's the work lost due to friction? So there's going to be no work lost between A and B, but from B to C, there's work lost due to friction from here to here. And that distance from there to there is 9 meters. How do I know it's 9 meters? It tells me. It slides for 9 meters before coming to rest. So if it's coming to rest at point C, then the velocity at C is equal to 0. Okay. And the potential energy at C, or the height at C, is 0. So we've got a situation here where we have 0 potential energy at C, and we have 0 kinetic energy at C. So clearly we have a situation where there is work out. Okay, so we got to use this energy formula again, except we will account for work out because there's going to be work lost due to friction. So I had to shrink these down a little bit, but here is our energy equation. We're searching for that work out due to friction, or the work lost due to friction. So we can start plugging in. You could either choose point A as your initial spot, or you can choose point B as your initial spot. Either one will work. And let's just label what kinetic energy at B is. We'll just move this up here. So we have our energies at B, energies at C, energies at A. We can plug things in here. Now, I'm going to take it, it doesn't matter where you take it from. If you go from B to C or A to C, because this part's frictionless, it doesn't matter. Okay, if there was friction here, and we need to account for that, that changes the problem up a little bit. But let's take it from B to C. It just seems a little more logical, a little more straightforward. So from B to C, B is going to be our initial, C is going to be our final. So initial potential energy is 0, plus initial kinetic energy is 58.9, and that's equal to our final potential energy, that's 0. Our final kinetic energy, that's 0. Plus whatever the work out or work lost due to friction is. And wouldn't you know it, the work lost due to friction is equal to 58.9 joules. So we've solved part B. There's the answer for B. Part A, we solved before. Here's the answers for part A. Kinetic energy at B, and the velocity at B is up here. So last thing we need to do is figure out what the coefficient of friction is between the block and the horizontal surface. And what's nice is that this is a flat surface, so we've got a situation here because we have a flat surface where force normal equals force weight. And the force weight, we know 2 kilograms is the mass of the object, so mg, 2 times 9.81. So I know force normal is equal to 19.6. And we're going to need force normal in order to figure out the coefficient because of that formula. Force friction equals coefficient of friction times force normal. Why do we need that? And how does that help us? We have to remember that work is equal to force times the distance or displacement. And we have our displacement of 9 meters. Okay. The force that's doing the work or taking the work out of the system is friction. Force of friction. So force of friction equals the work. We can plug in this for work. Force of friction we need force normal for in order to solve for the coefficient of friction. Work out, plug in here, force normal, we're going to plug in here, and our distance displacement we'll plug in here. Plug in those numbers, solve for your coefficient of friction. Coefficient of friction is going to equal 0.334, the coefficient of kinetic friction. A, B, C.